All right, folks, welcome back. It's section 1.4, Continuity and One-Sided Limits, part 2. We're going to start here and discuss two theorems involving continuity, the extreme value theorem and the intermediate value theorem. And we're going to do these by way of kind of introductory question and examples. Typically, I do this question and in this example as more of a classroom discussion. So the value of this won't necessarily come through as much on the video as it would if we were in the classroom, but hopefully you'll still be able to get something out of it. So first question here states, does every function have a maximum and or minimum value? Graph examples and counterexamples to support your answer. Well, let's just graph a simple function here. So I'd like to look at a function, just make it look like that, and we'll say that it goes from values a to b on the x-axis, and we'll go ahead and give it distinct endpoints. So I think that's pretty easy to look at that and say, yeah, I've got a minimum value right there. That's the lowest spot on the graph, and I got a maximum value right there. That's the highest spot on the graph. Could we do anything to kind of make this look different so that we didn't have a min and a max? So through the magic of modern technology, I've recreated the graph with one subtle change. It doesn't include the endpoint. So what I want to do now is show this graph as open circles at each end. So basically the difference between these two graphs is the one on the left is a closed interval. That function is defined on the closed interval from a to b. And the one on the right is an open interval. So using interval notation, that's a parenthesis rather than a square bracket. So the open interval from a to b means there's no min or max here, folks. I don't care how close you get to this open circle on the left. If you pick one point close to it, I can pick one point closer. Then you could pick a point even closer, and we could go back and forth forever and ever and ever and never reach that open circle. Same idea on the upper part there. So this function has no min or max. So it is possible to create a function with no min or max if it's defined on an open interval. For a closed interval, function defined on a closed interval, we'll find out in just a second about whether or not there has to be a min or max. All right, let's move on to the next thing here. It says, example, sketch a graph of your height from birth to age 17. No, you don't need to remember exactly how tall you were when you were born, just estimate it. So what your graph is probably going to look like is something like this. So birth is here, your current age for most of you, it's around 17. Oh, and I don't know, your birth height was, I don't know, some of you were probably 20 inches long, 24 inches long, somewhere in there. And then however tall you are now. And the graph probably looks something like this. So your birth height was here and you grew really fast, and then things started to taper out as you got older. And you're probably, if you're 17 years old, most of you are as tall as you're going to get. Sorry if you're not where you want to be. Okay, so let's take a look at this graph. To me, this looks like a continuous function on a closed interval. And if I asked you the question, were you ever 3 feet tall? Well, there's got to be a point in here somewhere when you were 3 feet tall. And it's not possible to physically be shorter than 3 feet one day and then taller the next. At some point you had to be exactly 3 feet tall. If I said, well, what about 4 feet tall? At some point you had to be exactly 4 feet tall. How about 5 feet tall? Yep, at some point you had to be exactly 5 feet tall. And that illustrates one of the two theorems we're going to talk about today. So let's move into those theorems. The first one is the extreme value theorem. If f is continuous, f is a function, if f is continuous at every point of a closed interval from a to b, then f takes on both a minimum and maximum on the closed interval. So let's just look at some examples graphically. I'm just going to sketch a couple here real quick. So if I have a function that does something like this, well, that's easy to see. I've got my max here and our minimum here. Now, what if we have a function that does something like this? Well, my max is there, but my minimum would be down here somewhere. And notice I'm sketching functions that are defined and continuous on a closed interval. What about this one? So that's a constant function. No matter what the input is, the output is the same. So we're going to make the following statement, because the theorem says if a function is continuous at every point of a closed interval, and this function, the one I've drawn, is continuous at every point of a closed interval, it has to take on both a min and a max. So for a constant function, that means the minimum equals the maximum. It's whatever the value of that constant output is. Okay, one quick reminder I want to mention here. I think I'm going to have to write this in the margin. Okay, so there's a quick note there. The word max or min in this definition, in this theorem, those mean absolute, not local, or sometimes we use the term relative. Let me note that here. Local max and relative max would be anywhere where we have a peak or a valley. Valley would be local minimum. So like in this graph here, this is a local max. This is a local min. Based on the graph shown, they also are the absolute min and max. But I just want to make sure you understand the theorem, as worded, talks about minimum and maximum. And anytime we say the word minimum and maximum, we mean absolute minimum and absolute maximum, not the local versions of those two. Okay, so that is the extreme value theorem, and I want to make one other comment here. In calculus, we take a lot of theorems, important theorems, and we abbreviate them with TLAs, three-letter acronyms. This one is EVT. So extreme value theorem is often abbreviated EVT. Just want you to be aware of that. Now let's move into a big one, the intermediate value theorem. The intermediate value theorem is fairly easy to understand, but it's pretty sneaky. It'll come up on you in a problem when you least expect it. In fact, in part 2 of the video here, I'll show you an example from the actual AP exam where you needed to use the intermediate value theorem. So what does the theorem say? It says a function y equals f of x that is continuous on a closed interval, so we're continuous on a closed interval, takes on every value between f of a and f of b. In other words, if y sub 0 is between f of a and f of b, then there exists a value c in the interval from a to b such that f of c equals y sub 0. Holy cow, that's a mouthful. So let's take a look at what we have here. So I have a graph of a continuous function on the closed interval from a to b. So notice those are closed points. Those are included in the interval. And then we have the output at each of those values. So a gives me an output f of a. B gives me an output f of b. So if we have some value y sub 0 that is between f of a and f of b, then there exists a value c, so c is going to be somewhere down here on this interval such that f of c equals y sub 0. So let's see if we can find that. If this is my y sub 0 value, then there has to be a c here such that f of c equals y sub 0. So that's the theorem. That is the intermediate value theorem, which again we'll abbreviate that IVT. That's intermediate value theorem. Let me run you through a quick example of how you might use that theorem. So prove that there is a 0 on the closed interval from 0 to 2 for f of x equals x squared minus 2. Well, hopefully, visually we ought to be able to figure out what x squared minus 2 looks like. we know that the graph of that function is going to be a parabola, and it's going to be a parabola that is shifted down from the origin by 2 units. So I'm going to go ahead and shift that thing down just to illustrate what that would look like. So that's what the parabola would look like, and we're going to prove that there's a 0 on the interval from 0 to 2. So we're going to prove that this 0, this x-intercept, is somewhere on the interval from 0 to 2. Here's what that proof might look like. In a previous lesson, we talked about how all polynomials are continuous on the real number line. So if we take just a small piece of that number line, the closed interval from 0 to 2, the polynomial will also be continuous on that interval. So just to compare what our theorem says, if the function is continuous on a closed interval, so we have to first state that the conditions required for the theorem exist. So I state that the function is continuous on the interval because it's a polynomial. Next, I'm going to state the following. For that function, f of 0 is -2. And I know that value, -2, is less than 0. I'm going to look at the other endpoint on the interval, f of 2. And if I plug in 2 to the function, 2 squared, or 4 minus 2, is +2. So I know that f of 2 is greater than 0. So I can make the following statement. -2 is less than 0, which is less than +2. So, by the intermediate value theorem, there exists a value c on the interval from 0 to 2 such that f of c equals 0. And folks, congratulations, you just used the intermediate value theorem to prove that there is a 0 on the interval from 0 to 2 for f of x equals x squared minus 2. Okay, I want to make a special note here. You'll notice that we didn't actually find c. We didn't find the value that gives us the 0. That gives us the 0 output. All we did is say that it exists. So that's an important note about these two theorems. So I'm going to take a little time here to make a note. Both of these theorems, EVT and IVT, they're called existence theorems. Okay, so what does an existence theorem do for us? So existence theorems can be used to prove that a value exists, but they cannot tell us exactly where that value is located. So what might that value be? Well, that value could be a minimum, a maximum, a 0, some value of importance to us when analyzing functions. All right, folks, we're going to shut it down now. We'll pick back up with the second page of the notes in part 2 of the video.